This video is about the code walkthrough of my project. First, I want to start with the note. The Goetzel algorithm code reference is from the GitHub repository I have mentioned below, and other two documentation I have referred to understand the Goetzel algorithm and adopt this GitHub open source algorithm. Next, I would start with the connection of the mic to the Arduino. I have connected the output pin of the mic to the analog input of the Arduino A0 VCC to 3.3 volts the Arduino, and ground pin of mic to the ground pin of the Arduino, and I have connected the analog reference of Arduino to 3.3. Next are the header files I have used. This is the servo motor library. Uh, this is kind of a class I have to instantiate to use certain functions to drive the servo motor. And the next one are the connections of L298N IC. That's the dual H bridge circuit through Arduino Uno. Motor 1 enable and motor 2 enable are connected to 9 and 10 of Arduino. These two pins are used to control the speed of the DC motors, and motor 1 in 1 rest all connected to the pins 2, 3, 4, 5. These are actually the output pins to the motor from H-bridge circuit. These two pins refers to the motor 1. This connect goes to the positive end of the motor, and the other one goes to the negative end of the motor. These two pins are actually enabled alternatively to rotate the DC motors in the forward or reverse direction. Similar approach is taken to the motor 2 also. And these are the pins associated with the ultrasonic sensor. The trigger pin is used to send out the ultrasonic pulses. The echo pin is to capture those reflected ultrasonic waves. And this refers to the servo pin 11 connected to the pin 11 of the Arduino. Rest all global variables I have defined. The block size I have set to 256 samples, and the amplitude threshold I have set to 20, and the frequency length is 8. So I'll explain this further when I go through the code. These are the global variables I have used throughout the code. This global variable refers to the frequency spectrum I'm going to capture through the to the mic using analog to digital converter with the Arduino. I've instantiated a servo motor class. This the actual table explains the concept of dual tone multi-frequency. Each keypad number in a mobile phone have a dual tone. This column uh, refers to the lower frequency end, and this row refers to the higher frequency of each keypad number. For example, keypad 1 has a lower tone of 697 Hz, and the higher tone is 1,209 Hz. I'll explain about this cosine and sine component when I go through the Goetzel algorithm main code. This is the structure I have created to store the detected digit. And this is the actual table which I'm going to map to the actual keypad numbers. Uh, I'm going to which I'm going to decode using the Goetzel algorithm. This part of the code is used to initialize the analog to digital conversion, the Arduino. These are like the code that's being, these are the values actually written directly into the uh, analog to digital converter registers associated to the particular microcontroller I'm using. This core part is what where the actual algorithm to detect the magnitude of uh, the frequency component in the spectrum I have captured. So with this coaxial algorithm, we actually compute the real and imaginary values in a frequency component. If you look at the variables I'm inputting to the coaxial algorithm function or the samples and the spectrum. Spectrum is actually the input which I captured through the A to D conversion. So within this algorithm, I compute the magnitude and phase value from the real and imaginary part. But in this algorithm, we are more concerned about the magnitude part, which is actually the amplitude of each frequency component, the captured frequency spectrum. So the cos term and sine term uh, are actually pre-computed before, which is mentioned over here. The cosine component and sine component are pre-computed, and this formula I used to compute the cosine component, and this is the formula I used to uh, compute the sine component. And the one important thing to mention is the sampling frequency I have used here is 9.6 kilohertz. So using the pre-computed values of cosine and sine terms, we I calculated real and imaginary part, and using those real and imaginary part, I computed the amplitude and stored in the spectrum array, where each value corresponds to uh, the amplitude of each frequency component in the spectrum. This function is used to compute the average of uh, the frequency component. So to better explain this, I have to start from this function detect digit, where the actual detection happens. So we compute the uh, average of lower frequency components and average of higher frequency components, and then we call the get index function with the actual spectrum we have computed in the quiet cell algorithm, along with the number of frequency components. Since there are total of 8 frequency components, so the lower four refers to the uh, refers to four lower frequency components, and we call the function get index spectrum to compute the average uh, and check for the amplitude threshold. Yeah, the amplitude threshold of the lower or computed actually using these two lines. The lower frequency average corresponds to the average of all four lower frequency components, and higher frequency frequency average corresponds to the frequency of uh, four higher frequency components, and we get the index of the frequency component so that we can uh, map with the table I have created above to store the actual uh, digit which has been transmitted by the user. And in this setup function, uh, we init the uh, COM port and we init the uh, A to D conversion, and this is the assembler instruction to enable all the interrupts in the Arduino. And this part actually sets the direction of each pin, whether it's input or output. Here we set the motor 1 enable pin, motor 2 enable pin, and the polarities of both the motors as output. And here we set the pins of the ultrasonic uh, sensor. The trigger pin is set to the uh, set to output mode, and the echo pin set to input mode. This is the piece of code that initializes the DC motor. So here I have initialized to uh, off mode of the DC motors, and here comes the auto collision detection I was talking about in the uh, project demo. Uh, Here, first I clear the trigger pin, and then I pull the trigger pin to high for 10 microseconds. That actually sends the 8 cycles of ultrasonic burst, and then I pull the trigger pin to low. The echo pin is actually red to see whether the waves are reflected back or not. The actual concept here is the echo pin uh, is pulsed to high. Uh, the maximum amount of time it can be pulsed to high is 38 milliseconds. Uh, so if any obstacle is found, uh, the the echo pin will be pulled to low automatically before 38 milliseconds. If no obstacle is detected after 38 milliseconds of being high, the echo pin will be pulled to low. This is the actual formula to compute the distance. In this software, uh, I have set that any obstacle within the distance of 15 centimeter, I consider that as an obstacle and stop the uh, robot immediately. That is stopping the DC motors and the servo motors. Here the main motor control. I have described what each keypad number and and its associated actions. The known issue I have is the power sharing issue between the DC motor and the servo motor. The speed of the motors cannot be run at any speed less than 255 duty cycle, uh, because if I operate the servo motor and try to reduce the speed of the DC motor actually stops. Better than stopping, I have currently uh, changed the intended usage of 238 keypad numbers. Right now, I'm running the DC motor at the constant speed for the keypad numbers 2, 3, and 8. The intended usage was to start the DC motor at a uh, set speed of like 175 duty cycle, uh, and then with 3, I intended to increase the speed. to 200, and with 8 I intended to decrease the speed to 100. So in this loop, first I start uh, to wait for the audio sampling to finish, and then I look for the collision detection. If the distance computed by the obstacle detection is less than or equal to 15, I say obstacle detected, uh, and I stop the motors altogether. That is putting the DC motors to the initial state. And if there is no obstacle, I run the coil cell algorithm to uh, extract the uh, spectrum, I mean frequency uh, component from the spectrum I have captured uh, using the A to D conversion. Then I detect the digit uh, using the function detect digit as I explained before. Below are all the switch case statements, like what action has to be performed for each keypad. For example, if the detected digit is 2, I enable the DC motors in the forward uh, direction with the maximum speed of 255 duty cycle. For 3, again I do the same action as 2, but the intended usage was to uh, set the speed for the keypad 2 to 175, and to set the speed of the DC motor to 255 when keypad number 3 is pressed. Use the keypad number 5 to stop the DC motors altogether. For 6, uh, I reverse the direction of the DC motor. For keypad number 8, again I'm running at the constant speed in the forward direction, but the intended usage was to reduce the speed to 100. Number 9, um, I used to uh, turn the servo motor to right. So, and I using the flag variables forward and reverse to see to set the DC motors again in the present state. If it's in the forward mode, then I again enable all the DC motors in the forward direction. If it's reverse, I enable the DC motors in the reverse direction. A similar approach I have taken for the keypad number 0. The only difference is when the keypad number 0 is pressed, uh, the servo motor actually turns to the left. So this portion of code I have used to print the uh, frequency spectrum uh, for the detected digit alone, not for all the uh, sampling. Only for the I print the values of the spectrum where I actually detect a digit. Here I resume the sampling interrupt. I mean, resuming analog to digital conversion interrupt. This is the interrupt service routine. In this routine is called whenever there is an interrupt by A to D uh, converter in the Arduino. As I said, I have enabled all the interrupts, including the analog to digital conversion in the setup itself. So at the start of the main body function, I wait for the uh, audio samples. So that's where uh, this is where I actually fill the samples buffer with the uh, value A to D conversion results. So I have set the block size to 250. Uh, so if the sample portion, I mean, if the buffer is full, I pull the interrupt to off. Like this body, uh, this this function body actually runs in a loop. So when it enters the loop, it again waits for the uh, audio sampling to finish and run the Goetzel algorithm, detect the digit, and operate the DC motor and the servo motor accordingly. And then it re-enables the sampling. I mean, re-enabling the A to D conversion. This is the actual comport I'm referring to. This is the example run uh, I have done, and in the code demo, I'll explain further about. Thank you.